The third approach we will talk about is actually the Kenny edge detector. The Kenny edge detector is a signal processing approach. Looking at an edge profile like this and assuming that there will be noise on the edge profile, a much more realistic assumption, we're looking for the optimal filter or optimal detector that will extract the edge in such a given signal. And the optimality is really defined in terms of good SNR, meaning strong response to edges and no response to noise ideally. Good localization, meaning edges should be detected at the right position, not before or after. And uniqueness, for given such a profile, I should be able to take only one edge and not multiple edges. So let's talk about this characterization a little bit. The first one was the SNR. So we want a system that actually responds to such an edge very strongly and respond to noise very badly. So if I actually talk about the system as H, I want a convolution of H with M. I can define it like this. Okay. So at the edge position, so assuming that the edge is actually at my origin in the x-axis, the response to the filter will be given with this formula here. Now, response of the same filter to pure noise, assuming that noise is actually Gaussian, white, and uncorrelated, can be characterized by the expected value given here. And the expectation is over the noise parameter. And if you do the math for this, you see that actually the expected value here at the edge location, meaning that x equals to 0, will give you something like this. Notice that this is the standard deviation of the noise model that we assume, and this is simply the square of the system, of the filter. Signal to noise ratio simply means that the response of the system to a pure edge and response of the system to the noise. So really, ratio of the edge response to the noise response. So that's the SNR. The second characterization was about the localization. So we want to locate edges at the right point. The maximum of the system response should really be at x0. And again, this is actually a stochastic process depending on the noise. Given noise, the edge actually might be detected before or after. So it will deviate from the ideal edge position. And in our model, that would be x equals to 0 at the origin of the x-axis. Now, the quantification through expected value of the deviation from the edge location is actually harder. So I will not get into the details here. But essentially, you want to look at the expected value given here. So the variation in the detected edge location. Now, this actually can be computed using this model. And notice that this is actually very similar to what we had before, except now instead of looking at the actual HM, we're looking at their first order derivatives. So really the convolution of the first order derivatives, and here I have the response of the first order derivative to the noise. So the match filter, or this optimal filter that we're looking at, should really be maximize SNR times the localization. And localization is defined by 1 over the expected deviation of the edge location. So maximizing localization means decreasing the expected variation. And believe it or not, the maximum of this is actually given by the signal itself, by the edge profile. So my system should actually be proportional to the edge profile that I expect. So essentially, it's identical to the system. And this is what's called the matched filter principle. You match the filter to the signal that you are trying to detect. For the edge model, this is given by differences of box filters. So given a profile like this, and you can see that it's actually quite noisy. You can observe that here, most of the values are negative, here, most of the values are positive. But it's quite difficult to detect the edge here around this point. Now, the ideal match filter looks something like this. Notice that this is the profile that we were always playing with. And we basically make it to 0 to make it a compact finite filter. If I apply this filter on this image, I will get something like this. Notice that actually, despite the noise, the highest area here really corresponds to the edge location. So indeed, the match filter is actually quite successful in identifying the edge point, even in this super noisy signal. But there is some problem here, which is while we solve the localization, so it's actually located at the right point, and we're prone to noise, so we achieve high SNR in the filter response, we expect to have only one unique edge point, while we got many of them. So how can we solve this problem? Again, this arises due to the stochastic nature of the noise. So to remedy this issue, we will minimize the number of maxima within the filter support. So we can characterize this by the average distance between subsequent zero crossings of the noise response. So if I take the filter, apply it to pure noise, and take the derivative, that should give me basically the points where the filter response achieves maximum. So the zero crossings of this, if I can actually make sure that the distance between them are high enough, then I can make sure that actually I get a unique edge response within the support of the filter. And this is given by something called the Rice theorem. So actually the average distance between two subsequent zero crossings in such a system is given by the power spectrum of the filter response, or the derivative of the filter response at the edge point, over the second derivative of that power spectrum. And the average number of maxima within a filter support, if I assume my filter is actually 2 times width, 2 times W width, then the number of maxima I should observe, expected one, is basically the entire support, or the width of the filter, over the average x, so the x given here. And I want to minimize this. I want to minimize the number of maxima that I observe within the filter support. So I update the overall goal for the candidate detector, and I say that now the overall goal is actually a linear combination of two criteria. First, I want to maximize the SNR times the localization, and then I want to minimize the number of maxima that I would achieve in the filter support. And notice that I have this value here. It's basically a coefficient that really weighs the contribution of these two different terms, and that is empirically selected. If I look at the result of that optimization for different C's, I can actually get an idea of what's happening. For small c, first of all, comparing the box filter to this, I see that this actually looks like the differences of box filter that I've seen before, the match filter, but it's somehow smoothed out. If I increase the c, I see that actually it's smoothed out even further, and if I use a large c, I see that actually it's very smooth. Actually, this optimal filter really resembles the first derivative of a Gaussian. And indeed, if I look at the filter that's coming out of the Kenny and the first derivative of a Gaussian profile, I see that they're almost identically the same. So it's nice because I actually, instead of computing this, I can simply use the differences of Gaussians. So let's take the noisy edge profile that we had before and apply this new filter to this. The result looks something like this. Now this is actually much better. Now compared to what we had before, we see that here, now I only have one maxima. It's really that I could locate the edge at the right point with a high SNR that actually has the highest value in this profile, and I only have one maxima, so it's unique. So in a sense, despite the noise, I actually could create a very successful edge detection for this guy. Now, all this discussion was assumed that actually we're in one dimensions, but we're not really interested in detecting edges in one dimensions. We're actually interested in detecting edges in n dimensions. Well, specifically, let's discuss the 2 dimensions. And the extensions to higher dimensions require certain assumptions. First, we had a very simplified edge model. So basically, we had this profile, that was going up. We assume that an edge really is given by a very simple profile given here. Now, extending it to higher dimensions means that I will still assume that profile by simply saying that, so in an image, there will be one direction to the edge, and I should only observe intensity variation only orthogonal to the edge. So I should see no intensity change along the edge. So that's kind of the extension of the simplified edge model to n dimensions. And this is an assumption that we require to be able to apply the Kenny filter. Second, 1D, although it's actually prone to noise, notice that in 2 dimensions or in higher dimensions, I can have noise in various different directions. So I will actually combine 2 different principles. I will basically be doing Kenny filter or edge detection in 1 dimension, preferably across the edge. And in the remaining dimensions, n-1 dimension, I will basically smooth the image to get rid of the noise. So I will use preferably a Gaussian smoothing operator. So the effective filter is really a directional derivative of a Gaussian operator. For example, it's given like this. In this case, I had the Gaussian and I take the derivative of the Gaussian in this direction. So notice that this profile looks like the optimal match filter that we see before, while this profile is simply Gaussian smoothing the image. Okay, so we will actually use such filters when implementing Kenny in higher dimensions. But the problems are actually not over, because we are working always on a discrete image raster. But the edges in an image can be in any dimensions, any directions in the image. So it's kind of a difficult problem. Now, there are multiple implementations that does interpolation of the edge in the image, basically trying to reduce the effects of discretization. But here we will talk about the faithful implementation by selecting the gradient direction that does not, by not selecting gradient direction that does not respect the discretization. So in estimating the derivatives in different directions, we are actually only going to estimate derivatives in 4 directions. Okay, so first we will smooth the image with a Gaussian filter. Image I, smooth it with a Gaussian filter. And then we will compute the derivatives in the north, northeast, east, and southeast directions. Really, the only directions that we can confidently and faithfully implement respecting the image raster. So we will compute the finite differences of the Gaussian filtered image like this. Okay? And notice that these are slightly different because the diagonal elements need to be corrected by a square root of 2 due to the difference between the distance is higher in this direction than in this direction. Okay, so we will actually compute these 4 derivatives at each point in the image, and then we will select the maximum as the gradient approximation. And we will keep the direction, one of these, as the direction of the edge. So let's see it a little bit in action. We had the image, the original image. On the right-hand side, we have the Gaussian smoothing version of it. And we apply the gradient approximation, and this gives us the gradient approximation. So for each pixel, we computed the 4 derivatives and only kept the maximum with the right direction. Fine. This is the first step. And notice that we don't really get very nice 1-line thick edges here. Well, that's because we're in 2D. All the Kenny principles applied in 1D, but in 2D, we need something more. So instead, we actually complement Kenny with post-processing steps. The post-processing steps are twofold. First, I do non-maximum suppression. At each pixel, notice that I actually had the gradient magnitude, but I also had the direction. So north, east, northeast, or south. North, northwest, east, and what were the directions again? Sorry. North, northeast, east, and southeast. Okay. Along those directions, I will actually look at the derivatives of each pixel. I will compare the derivative magnitudes at 2 neighbors along the selected direction, and I will only keep the pixels alive if they are actually higher than their both neighbors. So I will really suppress the non-maximal pixels. So this will already get rid of most of the results. So if I actually look at the result of this operation, I will get something like this. I took this image and noticed that in this image, there were quite a number of pixels per edge, so it was quite thick pixels. After non-maximal suppression, it looks something like this. Good. So now I get 1 thick pixels, but notice that I have a lot of edge pixels, and most of them are actually not true. Most of them are actually due to noise. So how do I get rid of them? The second post-processing step is what's called the hysteresis thresholding. So that's a fancy word for using two different threshold values, T low and a T high. So I will keep pixels, edge pixels alive, only if the result of the derivatives, f primes, are higher than T high. Then I will say that they are class 1 edge pixels. They have very strong gradient magnitude and they should be edge pixels. Next, I will discard all low magnitude pixels. So class 2 edge pixels, meaning that the derivative magnitude is really lower than the low threshold. So there is no way that they're edges, I remove them. But obviously, now there will be pixels that are between these two thresholds. And they're the class 3 edge pixels. And I will only keep them if their gradient magnitude is in between and they are connected to a class 1 pixel, possibly through other class 3 pixels. And this is required really to basically link the different edge pixels together, hoping to get clear boundaries of objects. So this was the result after non-maximal suppression. Now if I apply the hysteresis threshold, the result looks like this. So first, thresholding with the higher threshold, then thresholding with the lower threshold. So these guys are kept for sure, and all these pixels will be kept if they're actually connected to a class 1. And the result looks like this. Notice that between here and here, I got rid of some of the superior edges. And this actually is quite a nice result. I get actually clear boundaries in most of the objects. That's neat. Some remarks on the Kenny edge detector. So it is a state-of-the-art, non-learning based edge detector even today. It's very efficient implementation. And if you actually stick to the faithful implementation we discussed, then you don't even need any interpolation. If you want to basically be able to detect edges in any direction, then you need to interpolate in different directions the image, particularly for doing the non-maximum suppression. The post-processing, if you think about it, is the major contribution in this because the entire signal processing derivation led to simply using differences of Gaussians. It can be applied to any gradient-based edge detection. So instead of the difference of Gaussians, you could actually use a binomial filter, Sobel mask. That's completely fine as well. And it fails where the simplified edge model is wrong. So at crossings and corners, the simplified edge model doesn't really apply because I don't have change only in one direction. I have change in multiple directions. At those points, the Kenny edge detector can actually create gaps. And mainly these will be due to the non-maximum suppression step. They will basically kill each pixel because those pixels will not be maximum in any direction. And hysteresis thresholding is actually effective in 2D where the connectivity is well defined. In 3D, life is much harder. The last remark on this is probably on the more abstract topic of match filter idea. So this idea is very generic and can be used not only with edges, but with any type of pattern. For example, if I want to create a match filter for a line detector, it will actually look like a line. For example, this guy. You see that here I have high values in a background of lower values. Now, obviously, this will detect lines that are horizontal. If I want to detect lines in any direction, I would simply rotate this filter and apply it on the image. And that concludes our discussion on edge detection.